Okay, so we begin the second video of Introduction to Probability Revision, going over sample space, events, and Kolmogorov's axioms. Primarily what I want to focus on is Kolmogorov's axioms and what you derive from that. For sample space and events, what I've got here is some notation and some definitions, which I'm sure you're familiar with, hence the reason why I've wrote it down already, because I don't really want to bore you with this stuff. I believe I've got most of the things down. I might be missing one or two things, but I'm sure you can fill in those gaps. Just some things to highlight. We've got the two definitions. The sample space is a set of all possible outcomes. An event is a subset of the sample space. Just note that when we say elementary event, we mean an event which contains only one element, which is obviously a set with only an event with only one outcome, I should say, which is a set with only one element. That's what I meant to say. A or B, which is defined as at least one of A and B occur. These are his definitions, by the way. You might also see this rewritten as A occurs or B occurs, or A and B occur, and that's for A or B. Similarly, for asymmetric difference B, which is defined as exactly one of A and B occurs, you might also see this defined as A occurs and B does not, or B occurs and A does not. Just so you're familiar with, different ways that they can be defined. When we say the cardinality of A, we obviously mean the number of elements in the set A, and the probability of A is a bad P sign, I know, is the number of elements of A over the number of elements of the sample space. Okay, so what I really want to move on to is Kolmogorov's axioms, which are obviously very important, and you could straight up be asked to simply state all the axioms. You could be asked to perhaps state them in words instead of sentences. Kolmogorov's axioms. Let me just zoom in for this part of the video. Okay, so we'll let omega be a finite non-empty set. P as a probability function, obviously, and A as a subset of the sample space, which is obviously A is a set. And we say that the axioms say that the probability of A, any event A, is greater than or equal to 0. This is obvious because we're basically saying it's non-negative if you was to write it as without notation. And that's obvious because you can't have a negative chance of something happening. Doesn't make no sense. The second one, which says the probability of the sample space is equal to 1, because obviously the sample space is the certain event, as you may have saw on the previous page. So obviously the probability of the sample space is going to be equal to 1, because we know all probabilities go from 0 to 1. But assuming you don't know them, this is what these axioms state. And for the last axiom, we say that if AI intersection AJ is equal to the empty set, which is also can be said as pairwise disjoint, which is basically the mutually exclusive way of saying, or mutually exclusive for sets, basically, instead of probabilities. So if AI's intersection AJ is equal to the empty set for all I's not equal to J, then we can say that the probability of A1 union A2 union all the way to some finite number n is simply equal to the probability of A1 plus the probability of A2 all the way to probability of AN. So obviously this is just a recap. I'm sure you're familiar with all of these. And we derive some corollaries from these, which I will write down because just to add some little commentary about them, because they're quite important, because what they do is they can be used to prove a lot of things, and that's really an exam. What I'm kind of expecting is to be asked to prove something, and these corollaries or propositions can really help prove those. And obviously it tests our knowledge of these corollaries or propositions. So 3.1 Some of these are trivial, so I won't say much about them, but the probability of a complement is 1 minus the probability of A. Many times when proving things, or disproving things rather, it's a lot easier to start with a complement. I'll see if I can perhaps show an example in future videos of that. Let's see, 3.2, which is that the probability of the empty set is equal to 0. So that's, if I could just say it like that. This is obvious since, don't forget, we say that if this event A is equal to the empty set, we said that A is the impossible event, so obviously the impossible event is going to be allocated a probability of no chance of happening, i.e. 0 in terms of numbers. We have 3.3, which is that if A is an event, the probability of A is less than or equal to 1. There's many proofs where it might ask you to prove something. You might have to go from left hand side to right hand side, and there's always an inequality sign, and many times it's something little like this that will get you all the marks. But when you first see the question, you see this inequality sign, and you're thinking, how on earth am I supposed to get to that point? But something usually trivial as this, any event A is less than or equal to 1, obviously is something obvious, but it's a corollary that you should know and can help prove a lot of things. Let's see, and 3.4, if A and B are events, and A is a subset of B, so A, B are events with A being a subset of B, then the probability, probability of A is less than or equal to the probability of B. Again, this is, I guess, obvious when you understand sets. The probability is, since A is a subset of B, it's never going to be more than B. It can only be less than or equal to it, since it either has the exact same amount of elements as B, or fewer, so obviously the probabilities is going to be the same. Just two more, and these are quite important actually. I guess the corollaries aren't necessarily ranked, but 3.5 is very, very useful, although it appears, just kind of a simple or a different way of writing things. But if A is equal to it's a set of outcomes, basically, a finite set of outcomes, I should say, and it's a finite event. So if A is equal to this and it's a finite event, what we say is that the probability of A is equal to the sum from n I equals 1 of the probability of WI. Now this can be, although it appears, it's just another way of writing things, this can be very useful for proving things via induction, because when obviously proving things via inductions from algebra, you might prove it with a sigma notation, you might do that a lot, and so we can prove a lot of things like for n events by induction using this, and this notation makes it really easy to do so. Let's see, so we're nearing 10 minutes, so we have the inclusion exclusion formula for 2 events. Obviously all of these are stated without proof. 3.7 will be the only one I prove, since it's not in his lecture notes, but I'm sure it's probably in your lecture notes yourself, but I'll prove it anyway. And so we've got inclusion, exclusion. I'm missing an L. solution exclusion for two events. And that's for any events A and B. We have that the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersection B. Now obviously most of these can all 3.1 to 3.6 or they can be proven quite trivially and stuff like that, either using Kolmogorov's axioms or something else. And all of these are proven stated in the lecture notes, hence the reason I haven't really proved them. But 3.7 I'll just prove probably in another video because this has reached past the 10-minute mark. And so yeah, these are essential to revise, and when you go into the exam you should know all of these off by heart because you can be asked to use them. And a question might not explicitly ask you to use these, but it's very, very useful in many scenarios. And yeah, I think that will conclude the second video. I'll have the third video proving 3.7 and also doing some examples of where these are used, just so you're familiar with what I mean by they can come up as exam questions.